The third type of dependency is called as data dependency. It mainly happens because the instructions need some data and then they will write some data. Okay, I'll take an example and explain you. First, this type of dependency or hazard is called as data dependency or data hazard. Okay, and there are mainly three types of such hazards. So one hazard is called as read after write hazard or read after write dependency, and the second one is called as write after read dependency, and the third one is called as write after write dependency. So we have already seen such type of examples in databases also while dealing with the transactions. They are exactly the same, but then here we'll, instead of talking about the transactions, we'll talk about the instructions. If you have already watched it, there is no need of watching it. If you already watched it, you can observe the correlation between them. Okay, so there is no need of that knowledge at all. I'll start from basics and teach you. But anyway, I'm trying to say is there is already some connection there. If you can observe it, it will be easy for you to understand. So this one is also called as true dependency. Other name. See, data hazards are of these three types, and this hazard is also called as true dependency, and this hazard is also called as anti-dependency, and this hazard is also called as, I think, write dependency or output dependency. Okay, so I'll take examples and explain you. Let us say there is an instruction, and the instruction is like this: R1, R2 plus R3. Let's say this instruction is II, and then there is an instruction, and this instruction is following II, and this instruction is R4 needs something like this. Now if you observe this, whatever is written, whatever is computed into R1 by this instruction II is used by the next instruction IJ, right? Now the problem with this one is, in case if this particular instruction has not yet been completed, and if this particular instruction is trying to read that value, then it will read a wrong value. Got it? So if you want to see it, maybe you can think of it like this. Let us assume that we have a 5-stage pipeline: 1, 2, 3, 4, 5. Okay, so stage 1, stage 2, stage 3, stage 4 and stage 5. Okay, now this particular II is going to be executed in this one. Now IJ is going to start here. Stage 1 of IJ like this: S1, S2, S3, S4 and S5. Okay, now the value of R1 will be stored into R1 only after the execution of the 5th stage. Let us say this is the stage where write back happens. So whatever is being computed, it is going to be written back there. Okay, just for the sake of understanding, let me give some names to these stages, that way we will understand it better. Assume that it is instruction fetch / decode. So fetching and decoding of instruction happens in S1, and assume that it is where operands are being read. Okay, operands are being read, and in here it is executed. Instruction is executed, and if there is any kind of memory access, it happens here, and finally write back is going to happen here. If you remember, we have already discussed this type of pipeline in one of the videos. Okay, so now coming to the meaning of this, for this instruction, it means that we have to fetch it and decode it here in the first stage, and the second one is we have to read the operands, which means we are going to read R2 and R3 from the register file, and we are going to provide them as an input to the execution phase for the next one, which means this one. Now by the time I start S3, the inputs for this S3 are being fetched from the register file at S2. Got it? Therefore, in order to execute this, we can go ahead and execute it. Now whatever result is computed, that will still be inside the ALU phase in its output register, and that particular result will not be available in R1, right? And in case of memory access, we are going to use this, but for this instruction, since there is no load or store, we are not going to use memory. This phase is simply idle, and by the end of this phase, we are going to take whatever is computed as a sum of R2 and R3, which is R1. Only at the end of this phase we will be storing it back in the actual register R1. So till this phase is completed, the value of R1 is not going to be available. Got it? Now let's see what happens if I start second instruction. Now it will just fetch and decode it, and here it is going to fetch the operands. So which means the operand value R1 is not available till here, but it is going to, even before operand R1 is available, it is going to read a wrong value of R1 and it is going to provide it to the execute phase. Therefore, there is a chance that it is not a chance, it is definitely possible that whatever you are going to provide to the ALU here is a wrong value. It is not the right one. Now if you observe it, the reason why this has happened is this instruction has to wait until this instruction has written, which means it should read after the write. So since it is not doing it, it is a problem here, right? So because in order to handle this problem, you have to postpone this particular execution phase, or even this operand fetch phase till this point. Got it? So what is the solution? You should not start this. You should start S2 again here. S2 has to be started here, and then S3 like this. Got it? So till you finish the execution, you are not supposed to fetch the operands. This is the problem with this. So this is a dependency which is going to lead to some kind of problems, right? And this dependency has occurred because we are not waiting until until it is written. So that is why it is called as read after write dependency, right? And the next type of dependency is write after read. So this is a special type of dependency. So assume that we have some instructions like this, II and let us say IJ, some two instructions which are consecutive like this, and say we have let us say R1, R2 plus R3, and let us say there is something called as load some memory element into R2, which means we are trying to load something from memory into R2, right? So say we have a pipeline, we have a kind of pipeline here in which this particular value, this particular sum is going to be loaded into R1. Assume that here, okay? So this is operand fetch, let us say, and this is operand instruction fetch and instruction decode, and assume that there is some other activity is going to happen here. So reading operand read, okay? So because of some reason, let us say this operand decode is going to take a lot of time here, 2 cycles, and it is going to take 1 cycle, and it is going to take 4 cycles, something like this, and the next instruction has to start here and say before the operands are being read, if this is going to be changing, right? So which means this particular II has to read a old value of R2, but assume that because of some uneven delays in the pipeline or the way the pipeline has been constructed, it might so happen that before this particular instruction has read the value of R2, it is being updated. Are you getting this? Let us assume that initial value of R2 is 10, right? And this particular instruction is going to change it to 20. So but then this instruction needs the value of R2 as 10, then only it will be right. But then because of the pipelining and the way pipeline is being constructed, I am not able to show it clearly here, but assume that it is being constructed in such a way that even before this particular value is being read into this for this execution, the value is updated. So value has to be updated later, but assume that it is updated earlier because of the pipeline execution, right? Then such a dependency, again because of this there will be a problem, right? Then such a dependency is called as write after read dependency. The reason is you are supposed to write after this read, but then you are writing first and then reading is happen. That is why it is called as write after read dependency. And the next one is called as write after write dependency. So what is this write after write dependency is, let us say you have instruction I, two instructions like this, and R1, R2 star R3, and then R1 is, let us say, R5 plus R6. Now if you observe it, both are trying to write into the same register, but then this instruction has to write into it first and then this instruction. But assume that our pipeline is designed in such a way that this instruction is going to take a lot of time compared to this instruction. Multiplication is going to take a lot of time compared to this instruction. Therefore, when you try to execute them parallelly, this instruction will execute first and then this instruction, which means say if the value that is computed by this instruction is, let us say 100, that is computed as R1, and the value that is computed by this one is 200, assume that. Now if these two instructions are being executed in a correct manner, then the value of R1 has to remain as 200, because what happens is into R1, if everything goes on well, first this instruction will execute and which will write 100, and then this instruction will execute and which will write 200, isn't it? If everything goes on well, by the end of these two instructions the value in R1 has to be 200. But if something wrong happens, then what happens is this particular instruction will execute first, which means 200 will be written first, and then this particular instruction result will be written into this, which means 100. So this type of dependencies, they are called as write after write dependencies or output dependencies. Got it? So anyway, whenever there are these dependencies, we are supposed to delay the pipeline, or introduce the stall cycles, because of which performance is going to get affected. There are certain solutions for this. We shall look into the solutions. Before that, let's see how we can identify whether there are dependencies or not. Okay. So every instruction in general will read some operands and they will write some operands, right? So whatever they are going to read, let us call it as domain, right? So which means domain of II means whatever operands it is trying to read, and then range of II means whatever operands it is trying to write. So in this case, if you observe this one, in this case the domain of this particular II is R2 and R3, isn't it? Because that is what it is trying to read, and the range of this instruction II is R1. Are you getting this? So whatever you are trying to read, we call it as domain of that instruction, and whatever you are trying to write, we call it as range of the instruction. In that case, these are the same, right? And similarly, if you look at this instruction ij, what about domain of ij? Domain of ij is R1 comma R5, because this is what we are trying to read, R1 and R5. And what about the range of ij? Range of ij is we are trying to write into R4, therefore we are going to put R4, right? And now how can we identify these dependencies once we define this domain and ranges like this? So how to identify read after write dependency is, see this. So read after write dependency will be there whenever you are trying to write something and the next instruction wants it, right? Which means if the range of II, which means this one, is required by the domain in ij, intersection domain in ij. Are you getting this? This is the range of II and this is the domain of ij. If there is anything in common, which means if it is not equal to 5, what does it mean? So one instruction is trying to write something and other instruction is trying to read it. If this is the case, which means if there is something common between them, then we can say that there is a this read after write dependency. And remember that in this case II and ij have to be in this order, which means II has to be above ij. In that case we can declare that there is a read after write dependency. And what about this write after read dependency? Okay, I think I have erased the example. I'll just write it here. So write after read dependency occurs like this. If there are two instructions II and ij, okay. Now assume that this instruction R1, R2 plus R3, this instruction is trying to read R2, and before it reads it, let us say the next instruction, let us assume that the next instruction is trying to R5 R6 without confusion, is trying to update it, right? So then this will lead to write after read dependency. So how will it happen? Let us say assume that it happens. It doesn't happen in most of the cases, but assume that the pipeline has been designed in such a way to enhance the performance that these type of dependencies are introduced into the pipeline, in case they are introduced. Okay, so what does it mean? If II is trying to read a value which will be updated by ij even before it reads it, then only it is going to lead us to write after read dependency. So how can you write it in in those terms of range and domain? See this is domain of ii intersection range of ij. If this is not equal to 5, right, then this will lead us to write after read dependency. And what about write after write dependency? Both the instructions are supposed to write, even in this case also, write after read dependency also, II has to be before ij. This is the order, II and ij, this is the order. II has to be before and then this one has to be after it. And what about write after write dependency is, both of them are trying to write into the same register or the same operand, but one instruction which is supposed to write later is going to write it in the earlier, okay, earlier to the other one, prior to the other one. So how can I write it? Both are going to have the range only. II intersection range of ij is not equal to 5. So these are the conditions. You need not by heart them, they are so logical, I guess. You can simply remember it even mugging up. Okay, there is no need of by hearting it. Now there are certain solutions which are proposed in order to decrease these stall cycles. So if you observe this, in this case we are supposed to stop the operand loading till this spot, but then there are certain solutions which will help us without without even having these stall cycles, we will be able to perform the operations. We shall see what are the solutions. Okay.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply. And statement of purpose building. and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.